All right, what do we got going on here? Sorry for the little pause there. We have this prompt that says, as shown in the figure above, the function f of x consists of a line segment here. That's what it's talking about. That's a segment, straight line. And 1/4 circle, so that's a quarter circle. 1/4 circle. What is the average mean value of this function? Okay, average value. That has to do with an integral. The average value is basically the area, but then divided by that distance that's traveled. Well, what is this distance? It goes from 0 to 12. So we're basically going to have this integral from 0 to 12 divided by 12. Well, that's not too hard. Well, let's split this up into two things. So this first area, we got 4 high by 8 wide, so that's 4 by 8, that's 32. This second area, it's a quarter circle, and the radius of the circle is 4. Okay, well, if it was the area of a circle with radius 4 would be pi times 4 squared, which is 16 pi. But we're doing a quarter of that, so the area of a quarter circle is going to be 1/4 of that, which is just 4 pi, which is approximately, if you really want to get picky here, what's 3.14 times 4? I don't even need a calculator. I'm doing this faster than a calculator would. What? Check that out. Whoops, made a mistake. 5. I think, is that right? Then we got 4 times 3 is 12, plus this. So altogether, total area, this is about 12.56, I think. 12.56, there we go. Put that together, we get 44.56. 56. And some people might be thinking, well, but that's not the answer. And this 41 is kind of close, but then we got to divide that by 12. So I can almost look at this and kind of guess what is the average value of this. I feel like I'm missing something. Well, let's see if we can calculate this. The integral from 0 to 12, and then we have this other stuff, and then we're dividing by 12. Let's see what we can get. Okay, so the total area is 32 plus 12.56. Actually, you know what? Let's go back and do this. 3 times second pi, just because I feel like I'm not getting something. Whoops, 3 times second pi. I don't know what that was. Oh, whoops. No, 4 times plus another pi plus second pi. There we go. 12.56. That was right. Okay, so 12.56 plus 32, and we get 44.56. Then we divide that by 12, because that's our total distance. Oh, there it is, and we got 3.71. Bam! B is the answer. Bam, bam. Bam-a-lam. All right, what's next? 41. 41. If f is the function defined by f of x equals this, and g is the antiderivative of f such that g of 5 equals 7, then g of 1 approximately, ooh, that's rough. F is a function defined by here. G is the antiderivative. So g equals the antiderivative of f, and g of 5 equals 7. Okay, so that means we got to figure out what g of 1 would be. Well, I know this is one of those, it's called an impossible integral. Here's how we do it. Let's say we set it up an integral from 1 to 5 of f. What does that equal? Well, that equals g of 5 minus g of 1. We can calculate this side using a calculator, and we know g of 5 equals 7, and then we'll know the mystery. What's g of 1? Well, let's do that then. So we got to calculate this business. We got to plug in this function. I'm going to clear out these 3 functions. We're done using them. And now we got a new crazier function, cubed root of x squared plus 4x. All right, so cubed root, so that's, let's put in x squared plus 4x in parentheses. X squared plus 4x and then raise that to the 1/3 power because that's what the third, whoops, 1/3 power because that's what a cubed root is. All right, there's a function. And we're looking for the integral from 1 to 5. So my window, I need to make sure I'm going from about 0 to 6 or 1 to 5-ish, somewhere in there. Here's my graph. And it goes off the screen, but I don't really care because I just need to calculate the integral from 1 to 5. So I do second, calculate the area number 7 from 1 to 5, and that gives me 10.88. So this over here, this is 10.88. So 7 minus g of 1 equals 10.88. At this point, you should notice something. To get g of 1 by itself, I got to move that over to the right, 10.88 on the other side. 7 minus 10.88. What are you going to get? It looks like 3 point something. So let's just calculate just to make sure. Clear this. 7 minus 10.88. Looks like we get A is our answer. That was awesome. Quick and easy, but still very calculator-like. The amount A of t, a certain item being produced in a factory, is given by this, where t is the number of hours of production since the beginning of the workday at 8 a.m. Okay, so right here, this is t equals 0 when we start. At what time is the rate of production increasing most rapidly? Okay, so this is the amount. It's asking when is the rate a max? Okay, now this is trickier than you would think because you would be like, oh, so you just find when it's a maximum value. No, not quite. It's when is the rate a max. So we got to do two things. First, we got to take the derivative. Then we got to find the max of that. So let's find a prime of t. We're trying to find when is a prime of t a max. At a max. Well, let's do that. So we got a prime of t equals. We could do this honestly by looking at it, but I think it'll be a little bit faster if we do this. The derivative. This is 48t minus 3 equals. So that's just 48 when we take the derivative of that part. But this next one, this is kind of a chain rule, so we're going to have negative 12 t minus 3 squared times 1, which is really just negative 12 times t minus 3 squared. So minus 12 times t minus 3 squared. All right, so I'm going to plug that into my calculator. That was the derivative. 48 minus 12 times, well, it's x in this case, but tx, same thing. T minus 3 squared. Raised to the squared. Done. Quit. Go to. What does it not like? Oh, it doesn't like this extra little thing here. Delete it. Graph it. Whoa, it goes big. I think we need some big numbers here. Window. Can we zoom fit? Is there a zoom fit? No, it's not really a zoom fit. Okay, so then let's, I don't know, x maximum, let's say 5. Okay, but what about the y maximum? That's going to go huge. We'll start it at 0, but then let's go to like 50. Hey, oh, check that out. That happens right there at 4. That's 1, 2, 3. At 3. At t equals 3. At t equals 3 it happens. But when is t equal to 3? Well, t equals 0 is 8, so t equals 3 is 11 a.m. Boom. Whoops, wrong one. Did we skip one? Yeah, we did. There it is. 43. At how many points on the curve does this, will the line tangent to the curve pass through the origin? Oh, that's not too hard, I don't think, especially because we have a calculator. So I got to graph that thing. Let's graph it. Ooh, that's going to be hard. So it starts out 4x to the 5th minus 3x to the 4th. So 4x to the 5th minus 3x to the 4th. And then we got plus 15x squared. Did I press the x? No, not yet. X squared plus 6. There we go. We got it. We graph it. Oh, we need more picture than that. Does it say anything about an interval? No, it doesn't. So let's look at this interval in general. Let's just do zoom standard. How about zoom and then standard 6? We need to go bigger, it looks like. So let's change our window here to go from like, well, I did that same thing. I pressed clear. 10. Let's go from -10 to like 100. No, not 100. How about 50? Alright, so we have this curve, and how many times would the curve, the tangent line, be, well here, let's do this. I'll throw it in there. How many times would I have a tangent line that would go through the origin? So that looks like I could draw a tangent line that goes through on this side once, and then also on this side once. Whoops. Let's get a little bit better. A little bit tighter right there. So it looks like there's 1, 2 of them. B. 2. 2B. Or not 2B. Number 4. D4. A population grows according to the equation blah. T is measured years. This population will approach a limiting value as time goes on. During which year will the population reach half its limiting value? Well, let's just graph it and then see what's happening. So if I were to graph this, pull out my graphing calculator, we're going to have 6,000 minus 5,500 times e to the -0.159 times x. It says t, but it's really x. Alright, so do we need another one of these? There we go. Close enough. Alright, now for my window, I want to go way big because we're talking thousands here. So let's start at 0 and go to like 10,000. 1, 2, 3, 4, 1,000, 10,000. And for the Y scale, let's do it in thousands just to, kind of keep things a little clean. So now when I look at my graph, boom, there we go. It looks like we're reaching a limit here. What is this value? 1, 2, 3, 4, 5, 6. It looks like that's going to 6,000. Just to make sure, we can change our window here. We can go from 0 to 10. Let's say 0 to 100. And we're going to count by tens. Yep, it definitely flattens out. What is that line? It looks like it's 6,000. But let's see when if it is 6,000 for sure. So I'm going to graph a second line, and that would be 6,000. 6,000. Graph. Boom! Right on the money. How do we know that? Because we kind of have the 6,000 constant. That second term is going to go to 0 as t goes to infinity. That's kind of the math that's happening. Well, it says when does it reach half of that? Okay, half of that would be 3,000. So I'm just going to change this to a 3,000, like so. And then, check this out. Boom! They intersect. And we know how to calculate an intersection. Number 5. So let's move to that intersection. We're clicking, we're moving, and good enough. Second curve, yes. And it's at 3.81. Okay, so here's our picture. Here's what's happening. It's at 3.81, year 3.81. So in which year does the population reach half its limiting value? Not the second, not the fourth, but in the third. We don't round up to the fourth because it's still in the third year. So there we go, that's B. Last question, multiple choice, here we come. Well, this is like cockeyed. We need to rotate this business. Like that. That looks better. Alright, let's make this stuff big. Like this. It's like this and like that. Let f be a differential function for all x. The graph of f prime of x is shown. If f of 2 equals 10, which of the following best approximates the maximum value of f of x? Okay, This is f prime of x. The maximum value is not here. Not here. Because the maximum value of f happens when f prime of x changes from positive to negative, because that means that f changes from increasing to decreasing and you hit a max. So when does f prime change from positive to negative? That happens right there at 6. So we're really looking for f of 6. What does it equal? Okay, well, f of 6, this is an impossible integral, because think about it. I could do the integral from 1 to 6, and that is equal of f prime of x. That equals f of 6 minus f of 1, and I know what f of 1 is, right? No, not 1. This needs to be a 2. That needs to be a 2. So let's rewrite this. The integral from 2 to 6 of f prime of x is equal to capital F of 6 minus capital F of 2. And we know what f of 2 is, and we can kind of calculate this with squares and junk. So let's do that. Let's calculate the squares and junk. It's this area here. It's all this area here. Now I'm literally just going to count boxes, but kind of keep this in mind. See how the box here, this is 1 unit long, but whoa, this is 5 units long, so this one box is worth 5. And then we got another 5, that's 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 195. It looks like it's 95-ish. Maybe a little bit more, maybe a little bit less. Let's go 100. Let's just call it an even 100. So this is about 100. And f of 2 is 10. So f of 6 minus 10 is 100. You add 10 to both sides. Hey, look at that. We get 110. And you know, I kind of wasn't sure about that, but let's say I had guessed 95, which is for sure an underestimate. The only thing close to it is 110 anyways. So that is the answers. All right. That was awesome. That is done. See you in the FRQ.